Good morning. Welcome to the Art and Science of Light. Today we're going to do some experiments that I hope you can follow along with at home. And before we begin the actual experiments, a couple of housekeeping items. First, there's some additional resources in the description to this video that you can use to gain better insight and help you if you get stuck with some of the experiments. Secondly, there's an opportunity to comment after the video. Just press public comment and I will do my best efforts to reply to your video and help you if you get stuck with any of the experiments. Now, most of these experiments can be done with items that you already have around home, and if some cases where you have additional materials required, the sources will be listed in the description. Thank you very much, and let's get started with the Art and Science of Light. The thing I want to show you how to do is to project a rainbow anywhere you want in your house to make a decorative addition to your walls or ceilings. I'm going to use an ordinary CD-ROM. The ones that are marked CD-R tend to work the best, but any of them will work, whether they're blank or not yet recorded. Here's my setup. I have the CD laid flat on a table, and I have a very bright flashlight aimed down at a very steep angle, and I'm going to turn on the flashlight now and let you see what happens to the wall when the light goes on. You see an incredibly bright rainbow, and a couple of things I want to point out about it. You have the usual colors: red, orange, yellow, indigo, blue, and violet. And later on in the video, we're going to explore, in the last section in fact, well, what lies beyond the red and what lies beyond the ultraviolet that your eyes can't see, but we can make visible with some tools that we have. Now, the fun thing about this is that you don't need a flashlight. You can use the sun. And there's an interesting way that you can make a holder for your CD, and I'll show you how to make it right now. All you do is take an ordinary straw and tape it to one side of the CD. Okay, you take a second straw and you tape it to a square piece of cardboard at about a 40-degree angle. It's not critical if it's exactly at 40 degrees, but that happens to be the latitude of Columbus, Ohio, where we're recording this, and it's very important in astronomy, as we'll see in a minute. Then take another piece of cardboard, make corresponding cuts, slide them together so it makes a stand, and we can set it anywhere we want. And now if I turn it around, I can aim my rainbow by simply rotating this. And if I'm going to turn off the flashlight here. If you're going to use the sun to project a rainbow inside your house, it's best to find a south-facing window where the sun will be shining through the better part of the day. And what you do is you point the straw to the north. Then in the morning, you face the CD so the shiny side catches the morning sun, and then it will reflect it off at that same steep angle in this direction. And if there's a nice wall or a white piece of paper, you will get your beautiful reflected rainbow. And I'll include a picture after this segment that shows what a sun-projected rainbow will look like on the wall. But as the day goes on, you can rotate this to follow the sun. So at noon, when the sun is very high and shining straight down, it's still going to project the rainbow in approximately the same space. And then by sundown, when the sun is way back here, the sun is coming in from this angle and reflecting back to the same spot on your wall. So what you have is a sun tracker, and you might think of it as a reverse sundial, because however far you turn this corresponds to the time of day. Now, the way the rainbow projector works is that the CD disc has thousands of tiny circles on it that record the information for your music or whatever it's playing. And because those are so closely spaced together, when the light waves from the flashlight or the sun, which originally contain all the colors of the rainbow, hit those closely spaced circles, they cause the light to interfere with each other. And that interference, just like ripples on a pond, tend to either reinforce or delete certain colors at particular angles. And those reinforced colors show up very brightly as the rainbow. CDs make among the best devices to separate colors from white light that certainly I know of. But I want to show you one other demonstration of what happens when you take very closely spaced lines. And here, if you look in the center of this little disc, you'll see there's a clear plastic film. And while you can't see them because they're so small, they're tiny little lines traced all across this in both directions. And I'm going to take a source of light, and you can see it's a green laser that makes a very bright spot. But what happens if I shine it through these closely spaced lines? There you go. You see that we have lots of tiny points. If this laser was white, those points would be all different colors. However, because it only has green light, it spaces them out just like the rainbow is spaced out and repeated, but because it's only green, you get green dots. I'm sure that many of you have blown soap bubbles and had a lot of fun, but today we're going to look deeply into a soap bubble that's stationary. And I'm going to show you how to make a soap bubble viewer and explore some of the properties that make soap bubbles create the same types of rainbows that our CD did in the last experiment. All you need for this, and you can watch while we wait for it to pop, but all you need is a little dishwashing detergent. You see I have a small bottle of it here, mixed with water. I added a little glycerin so the bubbles will last a bit longer, but it's not necessary if you're just viewing them yourself. The other key elements, and while we wait to do the next one, is an ordinary straw, and you'll want to have a glass of water, because and the last thing is a little cup to hold your material in. Now, the most important thing for getting good viewing of the soap bubble is to use a dark or a black background. I've got a black piece of poster board and a black cap to hold the bubble, and a little stand to support it, but that's not really necessary. You can use anything from an ordinary soda can, turn it upside down, and you'll be able to blow the bubble inside the little depression that is underneath most pop cans. But let me show you the technique first. You want to wet the straw, because when a bubble contacts something that's dry, it tends to pop, and we don't want that to happen. You insert it, and you blow the bubble, and notice you withdraw the straw as you're blowing it. Okay? And now let's watch for a couple of things that are interesting and that you might do some things with, you'll see some swirling at the top. Actually, it seems to correspond with my breathing. If I blow on it, watch what happens. If I blow gently, you can see the swirling increases. Now, in the background, in addition to the colors that are the same as you see in the CD rainbow, you'll see a picture of the room in which we're taking, and it's like a fisheye lens, an extreme wide-angle lens. And if you adjust the lighting and the camera focus, you can actually use this to get some interesting photos. I'm just using an ordinary cell phone camera here. Oops, and there we pop the bubble. Let's blow it again. So you can see the method. And I'll change the lighting by turning on an additional light. And you'll notice, if you watch very carefully at this little bright spot, which is a ceiling light, whoops, you'll see that the bright spots tend to change as the colors change. Now, you'll notice the colors, after it settles down, tend to form kind of interesting bands across the bubble. And those bubbles, or those bands, tend to descend through the time that the bubble is active. You see that green band heading down toward the center, and the top of the bubble tends not to have as much color. The reason for that is the bubble is very thin, and it's comprised of 2 layers of soap with a layer of water sandwiched in between. There we're getting some nice swirling. And what happens is that gravity pulls the water down and it begins to evaporate, and it gets thinner at the top. Once it gets really, really thin, it can no longer reflect all the colors. And in fact, if you look at it from the top, let's see if we can hold it up here, you can see it becomes almost black at a particular point. There it is. See that large dark area? And when that dark area spreads throughout the whole bubble, eventually it gets too thin to support itself and will pop. There we're getting some beautiful swirls. Now the last thing I want to remind you is to look up, and I'll put a picture in here so you can compare. Have you ever seen a Hubble Space Telescope photo of the planet Jupiter? Well, I think you might want to look that up because the clouds of Jupiter have a pattern that is very reminiscent of the swirls that you're seeing on this bubble. So, and again, the reason that you get those colors is that the 2 layers of soap are separated by only about 1/millionth of a meter. And that's similar to the separation of the tracks on the CD, and it again causes the different waves of light to interfere with each other and reinforce some colors in some directions and other colors in other directions. We'll watch this just for a few seconds more, and then we're going to transition into making your own art creations with polarized light. Let me show you how to create some polarized light art. I think you'll find this very enjoyable and a great opportunity. I'm going to start with an ordinary plastic folder, and you'll see there's a faint outline of some little pieces of tape, ordinary cellophane tape, and I'll show you what type. I used packing tape, but ordinary any clear tape, the width doesn't matter, can work. Don't go out and buy a lot of tape, just test tape and cellophane packaging that you might get around a CD or a package of food even, might find that it works very well. But and this is an ordinary computer screen, and I've just set it so that it's mostly white. And I'm going to hold this in front of it, and you're not seeing very much. But now I'm going to take a pair of sunglasses and hold it over the camera lens, and what do you know? You get a very colorful image, and this looks a little bit like a butterfly to me. But watch what happens if I turn the sunglasses. The butterfly changes color from a brownish color to green to blue and back. Now, sunglasses aren't the only thing you can use to do this. These have to be a special kind of sunglasses called Polaroid sunglasses. But you can also use these small plastic squares, and they're called polarizing film. And in the sources of the video, there are places where you can buy them. They're not very expensive. For about $8, you can get enough of this film to make about 40 viewers. But you can see when I hold the viewer close to the camera and rotate it, the colors, seemingly by magic, change. And once I show you how to make these, I'll give you a brief explanation of how it works. And again, there's more details on the science behind it in the description. Let's look at one other image just to give you an idea of what is possible. Let's see what this looks like. I'm just taping it loosely here so I don't ruin my computer screen. Now let's adjust it a little bit. And let's hold the viewer in front of it. Whoops, it's a little bit too high. I think you can see this. There's a very interesting bird that changes color from yellow to purple to green, essentially many of the colors of the rainbow. And all this is a piece of plastic with small pieces of cellophane tape taped to it. Okay? Now, actually, before I show you how to make that, I want to give you some other little experiments that you can try. What would happen if I take an ordinary spoon, and let's move one here in front so I can hold it, an ordinary plastic spoon like you might use at a picnic, and hold it in front of polarized light. Now, it turns out that the computer screen is a source of polarized light, and it changes the direction that the light waves are vibrating. And the second polarizing screen that I have in front of the lens only allows light at a certain angle to come through. Let's look at something else. I have a little plastic test tube, and you can see that that has some color. Here's a little plastic magnifying glass, and notice how there's a pattern to the colors. What's happened is plastic objects are made by molding, and the manufacturer heats the plastic up till it's molten, injects it into a mold, and then pops it out, and it cools. As it cools very rapidly, the plastic gets stressed at different points, and the polarized light is a way to see how much stress that plastic has, and it can be used in quality control. Now, this is a ordinary CD case, and I'm going to hold it in front of the polarizer. And you can see there's certain points where the colors are concentrated, and notice that if I rotate the plastic, the colors change, or if I hold the plastic constant and rotate the polarizer, the colors change. That might give you some idea of how you can make moving artwork. And let's just take something very simple, just an ordinary piece of plastic folder, and I just drop some pieces of tape in. And you can see as I rotate they change. And also, if you notice up close what happens when you put extra layers of tape. If you have 1, 2, 3, 4 layers of the very thin tape, that change in the thickness also creates a color transition. So when you're designing your art, think about using more than one layer of tape. You can use up to 4, 5, 6 layers before it gets too dim to see. But that's something to experiment with. Now, a couple of things. Here are a couple of different approaches to designing your art. I always like to start with an outline and just take a piece of paper and sketch out. It could be an animal, it could be a geometric design, it could be something you see out of a window, anything that you think might be interesting if it became colorful. So what I then do is take a clear piece of plastic, and this is just a pocket folder. Doesn't really matter as long as it's clear and you can see your design through it. And then here you have two choices. Depends on how confident you are, but you can take a piece of tape, and let me show you. Here's a large piece of tape that I cut off that roll that I showed you earlier. And what you do is you fold it in half so it doesn't have a sticky side. And then, let's say I want to make one of this animal's legs. I cut a very thin section of the tape, and I figure out how long it needs to be for the leg, and then I can just lay it on there and move it around until I get it just the right size and shape that I need. Now notice it isn't sticky, so I can move and experiment, and at that point you can decide what it's going to look like when it's clear, and you can always hold it up in front of the computer screen with the Polaroid filter in front of your eye. You don't obviously have to use a camera to see what it's going to look like. If you're a little bit more confident, you can take the tape directly, and let's just do it that way. I'm just going to cut a very small piece of tape with the sticky side down, and I'm going to apply it to one of the legs of this animal. And now if I pick it up, let's reorient the camera. If I pick it up and put the polarizing filter in front of the camera, there we go. You can see that I've got what would be the back leg, okay? And as I rotate, it changes color. That's just with one piece. Now, if I were to add, let's just see what happens. I'm just going to add another layer over the top of that, and notice how the triangular piece was purple before, but now it has 3 different colors depending on which way it's rotated. So you can experiment with layering. Now, the other approach that you can use, besides whether to fold the tape over or just glue it down or tape it directly, is that you can take your clear overlay and use a magic marker and outline what you're going to do. And I'll show you how that might work. You know, you can just outline on the clear plastic and then go ahead and attach your plastic. Just tape it to the top of your computer monitor, or this will work on a television set, or even a tablet like an iPod or something. But whatever you do, don't tape any tape directly to your computer screen, because it's very difficult to get off and you'll probably mess your screen up. Okay. Now, there are a couple of other things you can try with polarizing filters. Let me slide the filter in front of the camera again. And here I've made a little animal out of a straw, out of a clear straw. And you see, if I hold it this way, its legs are green. If I hold it this way, the legs are blue. Based on, again, the angle and the number of overlaps, you can make 3D objects. And if I were to suspend this from a thread in front of the screen and let it rotate, you can have a rotating, color-changing 3D mobile. So that's a possibility. Now let me show you something else you can do with a polarizing filter. I've got a clear piece of plastic, and this is a little thicker plastic, and you notice when I rotate it, it changes color a little bit like the tape did. That's not too amazing anymore. However, notice I'm holding it in a particular location with my hand, and my hands are warmer than the plastic, so it's heating it up. And let's move my hands away, and as I rotate, you can actually see my fingerprints. It's retaining the higher temperature, and as I twist it, that changes the way the light twists as it goes through the material. Now, last thing that this plastic allows you to do is when I bend it, remember when I said that molded plastic stresses when it's cooled from the mold? Well, when you bend this plastic, it's stressed, and those stresses show up directly as different colors. So again, this is a way to that scientists use to test materials to see where they're going to break. I'm not going to try to break this plastic though. Okay, the last thing on this section of the Polarized Light Art video, I want to show you a little bit about how it works. I've just got a card with some slots cut out, a little bit like a picket fence. And if you could imagine light as a wave moving up and down, well, it turns out to be quite a bit more complicated than that. Not only does it move up and down, but the individual light waves can come out at any angle. And you think of it as they're moving forward, but different waves can be at any angle. Now, you'll notice if this cardboard is a polarizing filter, waves that are oriented this way can go through. If they're this way, they're going to be blocked. And if they're partially twisted, part of the wave can go through. Now, what happens if I put two filters together, or two polarizing films together, one oriented sideways, and if the light's coming through this way, okay, it gets through fine, but it's blocked by the second filter. So basically what happens is that when you twist it, some light gets through the first one and some light gets through the second one. When they're this way, most of the light gets through both of them, but when they're crossed, the light is almost totally extinguished. Now let me real quick demonstrate that with our plain computer screen. If I take two Polaroid filters, now if you don't have two, what you can do is, as we said, use the computer screen as, in effect, that's giving me one filtered light. As I turn it, if you look very carefully, you'll see the screen goes totally black and all the camera is seeing is the plastic filter in front. You see my reflection in back of it, and now it goes clear again. If you took your Polaroid sunglasses, if they were an old pair, and popped the lenses out as you put one lens in front of the other and twisted them, things would get completely dark or relatively light according to how you had them twisted. Okay, we're going to go next to our last segment of the video, which will deal with visible and invisible light, stuff that you think you can't see. Now let's take the opportunity to look beyond the ends of the rainbow. On the red side, we have a type of light called infrared, which our eyes can't see very well. And on the violet side, we have light that's called ultraviolet. Again, our eyes can't see it, but we're going to compare our human eyes to cameras on one side and different animals on the other, and maybe we'll learn how to make an ancient type of camera. So the first thing, let's take a remote control. This is an ordinary remote control that is emitting light in the infrared. And you see those two little LEDs. If I press the button, you'll see that they light up with a purplish light. Now, if I look at it with my eyes, I don't see anything. And I'd like you to try this at home. Get your remote control and just aim it at any video camera or cell phone camera. Now, I've found that this doesn't work as well with iPhones. Sometimes it works better with the front camera or the rear camera if the phone has two. But try it and see how sensitive your camera is to infrared light. Now, another object that's been in the news recently are remote thermometers. Now, this could be used to read if a person had a temperature several feet away. And right now, I'm just going to use it to read the temperature of this table, which is 68.9 degrees. Now I'm going to put my hand on the table, and I'll leave it for, say, 10 seconds. 5, 6, 7, 8, 9, 10. And I'll put it where my palm was. And now it's 71. So it increased the tabletop by a couple of degrees, and what's happening is the table is actually glowing in infrared light. In fact, all objects glow. Our eyes just aren't sensitive enough to see it. Now, let's turn to ultraviolet light, and everybody's favorite ultraviolet light target is an American $20 bill. And I've got a little flashlight that emits some ultraviolet light. And again, the camera is more sensitive. I can barely see a faint blue glow with my eyes, but the camera is showing it very brightly. And if you notice, right here, which is invisible in regular light, there's a faint, a bright line in ultraviolet. That's an anti-counterfeiting line that apparently is hard for counterfeiters to put on bills, but it only shows up with particular kinds of ultraviolet light. Now, how could you make an ultraviolet light detector yourself without any complicated equipment? And I'd like you to try this at home. And I did this because it was a sunny day yesterday. And I took a piece of black construction paper. Construction paper is best for this because it doesn't take very long, and put it out in the sun. And what I did is I put a CD, because it is opaque, it doesn't let light through. I just rested the CD on the paper for about an hour, and I get a pretty nice image of the CD. You can actually almost read the label in here. If I'd left it longer, I probably could read the label of the brand name of the CD. And you can imagine you can arrange as many different opaque objects as you would like on this paper. And if you're going to leave it outside for a couple of hours, you may want to weight the corners down so it doesn't blow away. But leave it at least 2 hours in midday sun, and I think you'll be impressed as to how well it works, and you can create your own designs this way. Now, what's happening is this is really only sensitive to the ultraviolet portion of sunlight, and it causes the dye to fade out or change color as the ultraviolet light breaks down some of the chemicals in the paper. Now, there's a commercial product called solar print paper that you may have seen in school or other places. It's not too expensive, and it comes in 5x7 sheets, and you can do the same thing with the paper, and it only takes about 3 minutes on exposure of bright ultraviolet light. Now, it won't work under room lighting because that doesn't contain enough ultraviolet light. But in any case, you can either use the solar print paper or ordinary construction paper, I think is the most fun to use. Now, another item that's kind of interesting is something called ultraviolet beads. And I'm going to take my ultraviolet flashlight and shine them on a few of the beads. And you see, let's dump them out so we can see better the plastic kind of getting in the way. There we go. Now we have some different beads, and these actually have several different colors, but they show one other property that I'd like to share with you. Do you see this one down here? You see how it glows even when the light's not on it? But then it dims really quickly. That's called fluorescent. And I think that was probably a manufacturing defect. When I light up the other ones, they change pretty rapidly. If I were to take these out in the sun, which contains even more ultraviolet, they change in just a couple of seconds to a very deep color. But I want to look at this idea of fluorescence. You see how that's changing color quickly under the light? Here's a jar of olive oil, and normally it has a kind of a clear yellowish color. And I'm going to take my trusty green laser. You can see it's got a green spot, and I'm going to shine it directly through the bottle. Now I want you to watch what happens. Okay, the green light changes to red when it goes through the olive oil. And what's happening is it's causing the molecules in the olive oil to vibrate in a frequency that, the atoms in the olive oil, to vibrate in a frequency that is at a different rate than the green laser. So it emits a different color of visible light. And the same thing is happening. The same thing was happening with that bead that was glowing when the ultraviolet hit it, but then stopped glowing when it was taken off. Now, the regular beads, when they're hit by ultraviolet, it actually changes the shape of the molecules so they reflect a different color of light. And it takes a few minutes for them to change back. You can see they've all changed back to clear or white at this time. So let's go on to the next experiment. Now, normally, you've heard that light travels in straight lines until it hits something. And when it hits something, notice you can see the laser going through the soap solution until it hits the wall of the plastic cup, and then it bounces back. And you'll see that some of it's coming straight through, some of it's coming through the other side, but basically it's reflected just like off of a normal mirror. So light travels in a straight line until it hits something. But what if I take something that's curved and shine a light through it? what if I take this coiled cable, let's put one end here, and I'm going to shine the laser light into one end, and because light travels in a straight line, it's not going to be able to go through, right? Whoops! It does go through. So light doesn't always travel in a straight line, or does it? What's happening is the light goes around just like it did on the soap solution until it hits it hits the edge of a different type of plastic in the cable, and that causes it to reflect once, and then it reflects off the other wall, and it reflects off that other wall, and it goes in a kind of a snake-like pattern as long as it doesn't bend too much. The inside of the cable is glass, and around that is another clear material that causes the light to reflect off the edges. And so it appears to be bending, but it's just going in a series of straight lines. Now let's look at another invention that's actually several thousand years old. It doesn't look like much. It's an ordinary cardboard box. Let me turn it over. And what I've done is put a small hole in one side, and I've cut out one corner. And what I'm going to do is, first of all, show you how you wear this box to make an ancient type of camera called the camera Obscura, which is up to a couple of thousand years old, and it predated cameras with film. So let me pause a second and show you what it looks like. Okay, notice that the hole is on this side. I'm facing away from the hole, and I'm putting my head in the box with the back toward the back, and now what I'm seeing is a view of the street out the window. And if I rotate my head, I can see the whole panorama of the sky. This is the camera Obscura. Now the interesting thing about the camera Obscura is because light does travel in straight lines, notice these lines that I've drawn. This is where the hole is in the front of the box. If I had an object out here, say a top of a tree, the light reflecting from the top of the tree is going to go down, go through the hole, go in a straight line until it hits a piece of white paper that I've taped to the back of the box. That's where the image is going to be formed. And light from the ground, for example, goes through this direction, heads up, hits the white paper in the back of the box, and shows the bottom of the image. So everything is going to appear upside down. Let me show you how it looks inside the box. In case you want to make these yourself, remember you tape a piece of white paper in the back of the box away from the hole, and the key is you face opposite the direction that you want to view. Now it's very important to have a partner when you do this. Don't put a box on your head and walk around and expect not to trip over something. So that's very important to remember. Now in the old days, before photographic film was invented, and certainly before video cameras and cell phone cameras, people would create entire rooms. So if you have a room in your house that only has one window, for example, and you could block up that one window and punch a tiny hole in the cardboard that you use to cover the window, your entire room would become the inside of a gigantic camera. And this was a fun thing that people used to do. They would get in the room, and after 10 or 15 minutes, your eyes get more and more sensitive to light. And even though the hole in the window would be very small, you would get a beautiful moving image of whatever was going on outside your house inside this camera Obscura room. Now, aside from having a helper when you use the camera Obscura, there's a couple of other details that will make it work much better. First of all, you need to seal up any holes in the box. Most boxes are going to have a small hole around the corners or along the seams, and I've just taped them up with some opaque tape. You can use masking tape or even dark paper tape with Scotch tape. Just make sure it's totally dark inside. And the second item is, even though there's a pretty small hole for your head here, you want to make it even darker. So what you do is wrap a sweatshirt or a towel around your neck when you put your head in the box so that it will block out additional light. The darker it is, and the longer you let your eyes adjust to the low light intensity, the brighter the image will be that you will see through your own camera Obscura. This concludes our light art video, and please keep me informed of your progress in doing some of these experiments. Really looking forward to seeing how you're doing. Okay, thank you.